Okay, so we're going to accept this. You can go through the proof of the similar situation with just this. So we're going to accept that the limit of a linear function of a vector x, this is really a vector x, x1, x2, x3, x so on. The limit of that as x goes to b, you can just drop, and b is again a vector, you can just drop the components of b in for the x's. Okay, now before we go on, we just want to make some concepts a little bit clear. So we want to talk about what we mean by the closed ball. So you remember open and closed sets. Closed sets means they include their boundary points, and open set means they don't. So that's the word closed here, and ball. So if we think about this, where a is a fixed point, a is some given point or some given vector. You can think of a point or a vector either way. And then we're talking about the set of all x's, and this is the length, so the distance between x and a is less than or equal to r. Okay, so that will give you a sphere. And then since it's less than or equal to, that means it's closed. So they call that a closed ball. So it's a sphere. I said a sphere, but that's if you're talking about 3D. But here we're talking about, we're going to actually right now they are just sticking to 3D, but we're going to switch to n dimensions. So before discussing the geometric meaning of the limit of a function, we need to introduce some standard terminology regarding sets of points in Rn. The underlying geometry of point sets of a space, the underlying geometry of that is known as the topology of that space. Recall from section 2.1 the vector equation where x and a are in R3 and r is greater than 0 defines a sphere of radius r. So this is when you have equal, then you get a sphere centered at a. If we modify this equation so that it becomes less than or equal to, we get what's called the closed ball. And if we use not less than or equal to, but just less than, then that's called the open ball. So this is for R3. There's nothing about the inequalities 1 and 2 that tie them to R3. In fact, if we take x and a to be points of Rn, then we can define 1 and 2. You can use 1 and 2 to define respectively the closed and open and dimensional balls of radius r centered at a. While we cannot draw sketches when n is greater than 3, we see what 1 and 2 mean when n is 1 or 2. So when n is 1, you just have an interval, like a closed or open interval. They don't show that here, so I don't know why she says we can see that. But for n equals 2, this is what it looks like. So you have two variables, x and y. So we're talking about 2 dimensions. And this is the closed ball, and this is the open ball. And sometimes they're called disks, especially if you're just talking about 2-dimensional. Okay, next we want to talk about what we mean by the boundary of a set in Rn. So you take a set of points in Rn, what do we mean by the boundary of that set? Oh, here are the intervals. Okay. Anyway, going back to the boundary of a set, suppose we have a set in Rn, and we want to define what we mean by an open set in Rn, and what we mean by a closed set. Now here, we call this closed, and we call this open. But more generally, how do we define open and closed? So here we mean that it contains the endpoints. Here we mean that it doesn't contain the endpoints. But when we're talking about greater than n equals 1, how do we define open and closed, and we'll do it in terms of this word boundary. But sorry, it says it's said to be open if for each point x in x there is some open ball centered at x that lies entirely within x. So if you go back to this picture, so if there's any point I choose in, if this is open, then any point I choose in here, I can draw a little circle around that point, and it will be entirely contained in here. Okay, you can find some small ball that will be entirely contained. So for any point, you can find some small ball that will be entirely contained in the set. If that's true, then it's called open. Now that doesn't happen here. It won't work here. So if I take a point right here, I can draw a small ball around it entirely contained in this set. So you might say, okay, that means it's open. But it has to be true for every point. And it's not true specifically for any point on the so-called boundary. So if I choose any point on the boundary, like right here, and I draw a circle around it, not every point in that circle will be in this set. So therefore, this set is not called open. So a point x in Rn is said to be in the boundary of a set. A point x in Rn is said to be in the boundary of a set x if every open ball centered at x, no matter how small, contains some points that are in x and also points that are not in x. So going back to that picture again, this is said to be on the boundary because no matter what circle I draw around it, no matter how small, I'm always going to get some points that are in the blue and some points that are in the white. Same thing with here. This is still called the boundary. So because any point in here, choose any point on the dashed line, and I draw, no matter how small a circle I draw around it, there are going to be some points that are in the blue and some points that are in the white. So some points that are in the set and some points that are not in the set. So therefore, those points are called the boundary. So now we know what we mean by the boundary. And then a set Rn is said to be closed. A set X in Rn is said to be closed in Rn if it contains all of its boundary points. So this one, the boundary points are this dark blue line, and this set contains its boundary points, therefore it will be closed. This set does not contain all its boundary points. In fact, it doesn't contain any of its boundary points, so it's not closed according to that definition. Okay? So that's what we mean by closed. Finally, a neighborhood, next word. Neighborhood of a point in a neighborhood of a point x in x is an open set containing x and contained in x. So a neighborhood would be, for example, here's a point A. What's a neighborhood of A? It's any open set that contains A. So this is an open set which contains A, so it's the neighborhood of A. Or you could draw some other shape, as long as it's open and contains A. That would also be called a neighborhood of A. Okay, now we can also say this. A set is closed if Rn, starting with the whole Rn, and subtract out that set if that is open. So let's go back to here. So this set is closed if and only if we take the whole space, subtract this out, and what we're left with is an open set. So that's true. If you take out this circle, including the boundary here, from R2, what's left will be open. Because if you draw, well, I won't go back through it, but it's open because of this idea of if you draw any if you draw any open circle around a point, if you take any point and draw a circle around it, some of the points in the circle will be in the white and some will be in the blue. So that's what this says. It's an easy consequence of the definition that a set X is closed in Rn precisely if its complement, Rn minus X, that's called the complement, is open. Okay, so here's an example. We're going to talk about points in R2, and we're going to put restrictions on X and Y like this. So restriction on X and Y is that X has to be between those two, and Y has to be between those two. And notice that all the less than signs are less than, not less than, or equal to. So really we're talking about this region here. So this is going to be open because if you take any point in here, you can find some small ball that is entirely contained in this region. The only places where you couldn't do that are right on the boundary, but the boundary is not included. So all of the points you can do that, so that means the set is open. On the other hand, if you did this set, including the boundary, then it wouldn't work. And in fact, this is the boundary here for this set. Okay, here's another example. The set X in R3 consisting of the non-negative coordinate axes is closed. So what they mean by, which set are we talking about? The non-negative coordinate axes. So this is the positive X coordinate axis, this is the positive Y coordinate axis, this is the positive Z coordinate axis. So that's a set of points, all the points that we just pointed to. So they're claiming that that is closed. So you can ask, what is the boundary of this set? So the boundary, remember, is the set, any of the points that where if you draw a circle around those points, you're always going to contain elements in the set and elements not in the set. So the set basically here is the black, and the stuff that's not in the set is the white. And if you draw any circle around a point in the black, you're always going to contain stuff that's not in the set, that is stuff in the white. So that means that the entire set itself is the boundary. There's no point in the set that's not in the boundary, because we just said that every point is in the boundary. Next, they say don't make the mistake of thinking that a set has to be either open or closed, because here's a set, and it's not open and it's not closed. Because if it's closed, it means that, if it's open, it means that none of the boundary points are in the set. Basically, that's one way to say it. But that's not true, because some of the boundary points are, but it's also not closed because it doesn't contain all of the boundary points, because all these points on the edges here are not in the set. So it's not open and it's not closed. Okay, so let's continue, and let's now use what we just discussed to give a geometric interpretation of the word limit. So we're talking about a function from Rn to Rm, but of course we can't picture that, so we're just saying this is the Rn and this is the Rm, or this is the Rm. Okay, so we have a set X, and we have a point in X. We will say that here's F, and that takes things from here to here, and we will say that the limit of F as X gets closer to A is equal to L if we can find like a ball around A, given any epsilon ball around L, we can find a ball around A such that everything in that ball in X goes within here. So if we make this ball smaller, then we can find a different, maybe we'd probably have to find a smaller ball around here, but we can find a ball around here so that everything goes into that ball. Okay, so they say, given any epsilon greater than 0, that is the radius of this ball, you can find a corresponding delta, that is a radius of ball around here, of radius delta, such that if the points x in x are inside this open ball of radius delta, centered at A, then the corresponding points f of x, all of these points, will get mapped, will remain inside this open ball of radius epsilon and centered at L. So that's the geometric interpretation of a limit when we're talking about from Rn to Rm. And let's read this, the definition of a limit. Given an open ball B epsilon, this is the open ball B epsilon, and all of this has to be open as part of the definition, centered at L, you can always find a corresponding ball B delta centered at A, so that points in B delta intersect X are mapped by F into points B epsilon here, the epsilon ball. This is called a delta ball and an epsilon ball. They also say that for this definition to make sense, the point A here must be such that every neighborhood of it in Rn, so every neighborhood of it contains points x in x distinct from A. So no matter how small a neighborhood you put around A, you have to have at least some points in X that are in there. In other words, if A was over here, then if you draw a really big ball, some of the points will be in X, and they will have to get mapped into here. But if A is over here, and you draw a small ball around here, none of the points will go into there, and so that doesn't really work. That doesn't really make sense. So anyway, we have to have, it says every point A must be such that every neighborhood of it contains points in X. So a point over here, some neighborhoods of it contain points in X, but not small neighborhoods of it would not contain elements in X. So a point over here is not called an accumulation point of X. But a point here, this is called an accumulation point of X, because every neighborhood contains at least one X. You cannot draw a neighborhood around A that doesn't contain at least one X. And of course, any point in here, that would also be true. But a point out here, some neighborhoods, big neighborhoods around A, would contain X, but some wouldn't. So it says that this A, when we're talking about the limit here, X goes to A has to be an accumulation point of X in order for this definition to make sense. So finally, from these considerations, we see that this statement, this limit statement, really does mean that as X moves towards A, f of X moves towards L. Okay, so that's like a very intuitive understanding of the statement of limit. As X gets closer to A, as X moves towards A, f of X gets closer to L. The significance of the open ball geometry is that entirely arbitrary motion is allowed. I'm not quite sure what she means, but I think that what she means is, I know what she means. So she means you can get close to A in all kinds of paths. Like you can go from here directly to A, or you can go from here, as long as you stay within the ball and go to A, you still should be getting closer and the value of the function should be getting closer and closer to L. Well, we'll see sort of why that makes sense in a minute. So let's look at example 8. So we're talking about this function. Now this function goes from where to where? Well, it has two inputs, so it goes from R2, and the output is a scalar, so it goes to R, but it doesn't quite go to R. They say it goes to, it goes to R, sorry, but it doesn't go from R2, actually, because we're not allowed to put 0, 0 into this function, right? So it's R2 minus the point 0, 0. Okay, so we just have to make sure that we say that, and then this goes to R. Okay, so now so this is the function we're talking about, and now we're going to do a limit problem, and they're going to say what happens as we get closer and closer to 0, 0. Now, 0, 0 is not in the domain. Here's the domain, and 0, 0 is not in there. But that doesn't matter. We're not concerned with what's happening at 0, 0. We already know that it's not even defined at 0, 0. But we're not concerned about what's happening at 0, 0. We're asking what happens as we get closer and closer to 0, 0. Can we say anything about that? Now, getting closer and closer, now it can mean not just coming in from the left or the right, but coming in from all different directions, right? We're in R2, we're talking about the origin. We could approach the origin from many different directions. But from whatever direction we approach it, it has to be, there has to be a single value that f gets close to. Otherwise, we won't say that there's a limit. Okay, so anyway, so let's start to explore this. So let's see what happens to f as x approaches 0, 0. Okay, note that f is undefined at the origin, although this is of no consequence insofar as evaluating limits is concerned. So even though 0, 0 isn't in the domain, we can still talk about limits getting close to 0, 0. Okay, now we're going to consider different paths getting close to 0, 0. So they're going to say, let's check out just coming in along the x-axis. So along the x-axis, that's when y equals 0, we calculate the value of f. So what is the value of f? So if we're always on the x-axis, that means y is 0, so we can replace all the y's with 0, and we get x squared over x squared, which equals 1. Thus, as x approaches 0 along this line, along the x-axis, the values of f remain constant and are always equal to 1, no matter how close we get to 0. However, now let's consider a different path. So along the y-axis, however, in the y-axis, then x is 0, then these two are 0, so you get 0, 0 here, then you get minus 1. So coming in along the x-axis, you always get 1, but coming in along the y-axis, you always get negative 1. So you can't, okay, so coming in along x equals 0 means the x coordinate equals 0, then the vector goes to 0, means that it's going to be negative 1. We just said that. In fact, the value of f is constant along each line through the origin. Along the line y equals mx, with m constant, we have, in fact, this is what you get. So when x is 0, you get one thing, and when y is 0, you get something else. And anyway, this is the general form, so we see that it clearly depends on the line by which we approach 0, or 0, 0. So therefore, there's no single unique limit. As a result, the limit of f as x approaches 0 does not exist, since f has a different limiting value depending on which direction we approach the origin. So that seems pretty weird, but that's the way this happens to behave. So it would be interesting to ask, what does a picture look like for this thing? And they say, see figure 2.39. So what is that? Where is that? So this is the picture. It's kind of hard to see, but you can sort of see that when you approach along this direction, it's always, I guess what they're trying to say is, it's always equal to 1. And when you approach in this direction, it's always equal to -1. And in other directions, it's something else. It's pretty hard to even see what this looks like. But that's what we're dealing with. We're dealing with, what was the function? It was this function, and that's what it looks like. Can't change that. Okay. So depending on the direction we approach, that is, no matter how close we come to the origin, we can find points x such that f of x is not near any single number L. So you can get, because you have to consider points from all directions, so you're going to get all kinds of different values for f. In other words, every open disk centered at 0, 0, no matter how small, is mapped into the interval between -1 and 1. So it's not a single number, it's going to be, you're going to be able to find values in this entire interval. If we graph the surface having the equation this, we can see quite clearly, I can't see very clearly, but that there is no limiting value as x approaches the origin. Okay, so this picture. Okay,